Welcome everyone to electrocatalytic conversion of CO2. In previous videos, we have mentioned the importance of reducing fuel carbon feedstock in the industry. In this video, we are going to introduce an emerging technology, the CO2 electrolyzer, which uses carbon dioxide as raw material and converts it into added value products. In the current video, we talk about CO2 co-electrolysis with water as an alternative industrial process that can support industrial defossilization. As a process that uses carbon dioxide, CO2 co-electrolysis can be classified as a carbon dioxide utilization technology called CDU. However, we know that using CO2 does not mean that the process produces zero emissions. It means that no CO2 is released. That this implies directly negative emissions. That means that it removes or sequesters more CO2 than is emitted, or that it generates lower emissions than the benchmark process. That is not for granted when using CO2, and a proper life cycle assessment calculations have to be done. CO2 co-electrolysis can produce chemicals through an alternative carbon source, carbon dioxide, and water, while consuming renewable electricity, possibly from the intermittent wind and solar power. With this slide, we would like to remark that the conversion of CO2 can happen in one step, when CO2 and water are converted together, or in two steps, when water is converted into hydrogen that will be combined with CO2 in a thermochemical process. Moreover, microorganisms can be used to convert CO2 into more complex chemicals. As a result, in all the cases, chemicals and fuels can be synthesized at different ranges of purity, which are generally low, and then these streams need to be purified before further use. Eventually, the CO2 emitted in the process can be captured and used again. This is a simplified outline of a CO2 electrolysis supply chain. To begin, the raw materials for the conversion process are purified. CO2 comes from an industrial point source or from the air, and water is usually consumed as ultra-pure. Once both feedstocks are available, they can be transported to the point of consumption. Renewable electricity should be available to power the electrolysis process. CO2 can be stored, and maybe you have heard about carbon capture and storage to mitigate climate change. Note that CO2 utilization potential as consumer of CO2 is much more small than the potential of CO2 storage. This slide represents the most important figures of merit, defined as the most commonly used lab-scale performance indicators in CO2 electrolyzers. The diagram shows an electrolyzer with two main inputs, pure CO2 and electricity, and the product yield as the output. Note that this is a simplified diagram, and the performance parameters are not independent of each other, and these are influenced by many other factors. The Faraday efficiency represents the selectivity of converting carbon dioxide into a certain product. Current density is the amount of electric current flowing through the electrolyzer. The equipment size represents the reactor dimensions. Durability refers to the lifetime of the electrolyzer. And the energy efficiency is the ratio between the energy stored in the desired products towards the input of electricity. There are four main types of CO2 electrolyzers: alkaline, proton exchange membrane, anion exchange membrane, and solid oxide electrolyzers. In electrolyzers, electrons flow between two electrodes, and these are separated by an electrolyte. These electrolyses differ from each other based on the electrolyte phase and the operating conditions, which at the same time affect the type of products that can be formed. High temperatures favor methane synthesis, while electrochemical mechanisms towards multi-carbon products are less favored. Variations between these types of electrolyzers include a specific reactor design, performance parameters, and technology maturity. The targeted products such as carbon monoxide, formic acid, methanol, ethanol, etc., significantly influence the plant's configuration, the scale, and the performance. The current and the following slide focus on high-temperature solid oxide electrolyzers. They use heat at 700-900 degrees Celsius. See in the image a drawing of a cell composed of two electrodes separated by an electrolyte that allows the pass of ions. The three of them are solid. The two electrodes are composed of different materials and can conduct both ions and electrons. Electrolyzers scale by number. See in the picture an example of the assembly of cells into small repeating units and into stacks. This slide presents different challenges taking into account the development of the whole electrolysis plant. Upstream processes should consider carbon dioxide and water conditioning to the electrolysis consumption requirements. The downstream process considers the mix of products, byproducts, and waste generated in the electrolyzer, because products must be separated to achieve the commercial purity. Future plants will be powered by renewable electricity, requiring flexible process designs to handle intermittent electricity supply. Flexibility at plant and equipment levels is crucial to manage fluctuations in product quantities and qualities. Flexibility at the plant can be managed by different strategies that you can see in the slide. Different strategies consist on different storage solutions, parallel lines of production, different size, and so on. To conclude, CO2 electrolysis is an emerging technology still under development. As a carbon dioxide utilization technology, it has the potential to contribute to the process industry transition as an alternative process to produce chemicals. Current challenges are technology development, plant efficiency and heat integration, and management of electricity intermittency. Thank you very much for your attention.